All right, so like I was saying, my name is Shri. I am your OChem peer tutor, and this is the first weekly review for exam 2 or unit 2. So we're going to go over exam 1, just discuss what went right, what went wrong, how's the format and everything. I'll start to talk about exam 2, look over the syllabus and kind of plan ahead. And then, of course, I'll get into chapter 4, which is your trends like radicals and etc. Carbocations, carboanions, like learning about primary, tertiary, secondary. And next week, we'll get into the actual bulk of Unit 2, which is your mechanisms. We'll start out with SN1, SN2, and then eventually we'll get into E2 and E1. Okay? So for now, in the chat, please let me know, like, if you guys have any thoughts on exam 1. I'm not sure if you guys got your grades yet. I don't think so. I mean, well, actually, it might be multiple choice, so it might have been instant. But okay. So someone said the OChem exam was okay. I was able to finish in time, but felt a little rushed at the end. There were a few questions that were tricky, where details might have been overlooked. Okay. Yeah, that is honestly a perfect reaction. That's probably the same reaction I had when I took OChem, the first exam. So I won't get into grades. Obviously, don't feel free to share it here, even though it's anonymous, but it is recorded, just a disclaimer. So your name won't show, in case you guys were worried about that. But yeah, thanks for sharing. I do think time does catch a lot of people off, especially since this was your first exam. It will take some growing pains. Hopefully all of those pains are over and you guys have a clear idea on how to study, how much time you need to prepare for the exam, and how much time you need to pace yourself during the actual exam. And yeah, there will be obviously a few tricky questions, so really pay attention to the entire question. Okay, anyone else have any other thoughts? I personally, this was back when I took OChem, we had drop exams instead of like the final replacing it. I think that's what's happening this semester, but this was my drop exam or my lowest exam. I personally felt like this exam was my hardest compared to like all of OChem 1 and OChem 2. So if you felt the same, don't be discouraged. You might feel the same and you might still end up with a really good score in OChem. Okay, and someone said, I feel like I needed more practice with ranking. Okay, yeah, we can definitely incorporate more ranking this unit in my weekly reviews. And of course, obviously, please come to peer tutoring whenever. Ideally, you want to come at least throughout the weeks leading up to the exam, and instead of like at the week of the exam, to give yourself enough time and to get like the proper time and energy you would receive, because on the day of or the week of the exam, there's going to be a lot of other tutors or students who have the same idea, but there's only so many tutors and so many students we can help with. But yeah, so OChem is, you have to have consistent effort. It's just like a math class. The more practice you do, the better you will be. All right. Looks like that's all everyone wants to share. So I'll get into exam 2. Let me actually turn on my camera. All right. I know my camera is kind of small, but hopefully it'll give you guys a little bit more personal approach. Yeah, exam 2 can be very tricky. I'll admit it is kind of subjective. You are dealing with a lot of components. You kind of have to put together a lot of pieces and get your result. You'll get into what you originally thought OCHEM was, which is reactions and like electrons moving around and attacking each other. So this is, I guess, a different approach and a fresh perspective compared to Unit 1 material. Unit 1 material had a lot of mini topics that sometimes correlated with each other, sometimes didn't. But Exam 2 is heavily related to each other. You'll be dealing with the same, I guess, realm of like concepts. Like I said, I would say about 70% is based on like chapter 6, which is like the mechanisms, SN1, SN2, and later on you'll learn about E1 and E2. And then the other 30% is like on chapter 4. So I understand. So it looks like you guys also have chapter 7 on your exam 2, just because everything kind of shifted over when they redid the syllabus. Chapter 7 is on alkenes, and we'll get into that when we get to it. That is in about 3 weeks or so, so we have plenty of time. But before then, I still believe chapter 6 will be a huge chunk, maybe like about 60%, and the chapter 4 and chapter 7 is about 20%. Obviously, don't quote me on that. That's just how I felt when I took the exam. So most of the time, you will be doing practice questions with these in this chapter. Of course, the other chapters as well. It's going to be a lot of reactions. It's going to be like a lot of one-on-one cases. But yeah. Okay, so any other general questions? Maybe like any questions on how to study or how to better prepare for exam 2 or where to start? If not, I'll get into chapter 4. Okay. Looks like no one has questions, so I'll get into chapter 4. So chapter 4 deals with radicals. So you'll hear, well, first of all, let me explain what a radical is. So a radical, give me 1 second. So I'm trying to keep everything on the same page so you guys can see everything. I'm just trying to see if there's a better way of teaching for this unit. So let's say, for instance, there are 2 hydrogens here, correct? And then, of course, each of the methyls have 3 hydrogens, okay? So for instance, let's say, well, basically anywhere there's a hydrogen exists a radical, okay? So if I delete this hydrogen and this bond and replace it with a radical, and you denote that as a dot, okay? So that period or dot, whatever you want to refer it to it, is called a radical. And radicals exist wherever there is a hydrogen, okay? So that's the first step of knowing what a radical is, okay? Now, there are 3 different kinds of radicals. Actually, before I get into that, let me also talk about what a carbocation is. A carbocation, and you guys should be familiar with this word before, is a positive charge like that. It's very similar to the radical where the hydrogen leaves, but the difference is the radical is like a partial separation, where the radical is like holding one component, like half of the electrons, because if you remember, each line is a bond, and in each bond there are 2 electrons, okay? So one of these electrons is considered a radical, okay? And in order for this one radical to become a bond, we need another single radical or another component, one single electron that can combine with it. But the difference here is, so if I were to show with arrows, it's like only a single electron leaves, okay? But here, once again, a bond and two electrons. If I were to show it again, it's that both of the electrons leave with the hydrogen, and you are left with a positive charge, okay? And if you remember, carbon has 4 bonds. It has 4 valence electrons. So if I count the number of bonds, valence electrons, I have 1, 2, 3, okay? It's supposed to have 4. 4 minus 3 is positive 1. That's why it has a positive charge here, okay? And this is called a carbocation. And let me actually write these names down. So this is called a radical. This is a carbocation. And if you guys have any questions or you want me to elaborate, feel free to just type in the chat whenever. Don't feel like I have to pause. Just ask whenever. Okay, and then lastly, we are going to talk about carboanion, which is a negative charge. Okay, so carboanions is you still have the bond. Let me see. Let me think about this. So first of all, let me write this down. So carboanion. So each carboanion equals a negative charge. Or yeah, it's a negative charge, but it also equals a lone pair. Okay. So we still have obviously a hydrogen, I believe, but we gain an extra valence electron. So we are gaining. Sorry, I'm getting a little confused with the semantics. So just don't get too concerned with the semantics, but just understand the concepts, kind of. Sorry, let me delete that. Okay. Yeah, this part, don't pay too much attention to it, but just trying to make me explain to you guys. Basically, if you have a lone pair, that means you have an extra charge, like an extra single electron. So like carbon is supposed to have 4 bonds, but with this lone pair, it has 1, 2, 3, and then 4, 5, which exists in the carboanion, which is a negative charge, which is also a lone pair. So all of that gives you that negative charge, okay? And obviously this is a positive charge, okay? And in fact, let me rewrite this as positive charge. Okay. This is a negative charge. Okay. All right. So now that we got that covered, I want to talk about primary, secondary, and tertiary, okay? And regardless of radical, carbocation, or carboanion, you will have to, you could have a tertiary radical, a primary carbocation, a secondary carboanion, and like all kinds of combinations, okay? So to explain that, I'm going to draw right here. Are you not able to hear me? Can everyone else hear me? Okay. If you're not able to hear me, I would. Okay, I obviously can. Yeah, I would recommend relogging. Okay, so tertiary, secondary, and have you guys, whatever I'm covering, you guys have covered it already, right? Okay, perfect. So this is tertiary, known as 3, I guess, kind of dot. So usually it's not like the star symbol, it's like the degrees. And then this is secondary, so known as S. And then primary. Yeah. One sec. All right, so I'm going to use radicals to explain. Or actually, let me use, yeah, okay, I'll use radicals. Okay, I'm going to use blue. So, okay, so understanding how to label like or look at a radical carbocation or carboanion and then say it's primary, secondary, tertiary is probably one of the most important skills you need for chapter 6 when determining which mechanism to use and which route and like which direction the reaction will take place, because each of these have different properties. Okay. um, so the way I like to tell people is to draw a arrow to the carbon that is attached to your charge. Okay, and we're considering radical a charge here. Okay, so this carbon is the one that I'm pointing to. Okay, and then the next thing you want to do, well, actually, let me draw my arrows for all of these. Okay, it's that carbon there and that carbon here. Okay, next thing I'm going to do is in I guess green, I'm going to circle all of the other carbons bonded to the carbon I pointed to. Okay, so I have one right here, and I have 1, 2 right here, and then I have 1, 2, 3 right here. Okay, I feel like some professors like to use like hydrogens to kind of denote it and maybe have the opposite approach. That is perfectly fine. This is how I personally got used to telling, and I feel like it's easier for me. If the other way is easier for you, obviously go ahead and use that approach. But yeah, so if you point to the carbon bonded to or contains your radical or charge, which is this carbon, and then circle all of the other carbons bonded to that. And notice I said only other carbons, okay? If, let's say, this was attached to a, never mind, actually. Okay, so because I only circled one carbon, this is a primary, 2 circles, secondary, 3 circles, tertiary. Okay, so I really recommend you guys doing this like in the early stages of this unit. Um, eventually you'll get to the point where you can just look at it and be like, oh, that's tertiary. Oh, that's primary. Okay. All right. So any questions about any of this so far? I'm just going over the most basic ones so far. Okay. Um, All right, so now we're going to talk about trends. And then we'll get into, so we'll also talk about bromination and chlorination within chapter 4. Okay, you guys haven't finished chapter 4, correct? Or have you guys started chapter 6? You guys finished? Okay, today. All right, perfect. All right. Yeah, next week we will definitely cover chapter 6. Okay. But yeah, this will probably just be a like summary of everything you learned for chapter 4 so far. Okay. Um, so what I mean by trends is I mean by ranking. So whoever said they needed practice with ranking, this will definitely help you get you kind of like a quote unquote cheat sheet that you can refer to when you're practicing, but obviously during a quiz or exam, you will have honor lock. But yeah, this will get you kind of a right start. Okay, so I am going to, sorry, I'm looking at my notes. So for radical, and carbocation, they have the same trend, okay? And the trend is, I'll type it out and then I'll actually draw it out, okay? So it goes benzylic, which is better than allylic, which is better than tertiary, better than secondary, which is better than primary, better than methyl, better than phenolic. Okay, let me see. All right, let's put that right here. Hold on, I didn't spell that correct. Okay, so just pretend I put work here. Dot. So that's the trend for that, and I'll actually draw what that looks like. I'll use carbocation to denote these. So benzylic, obviously, it has the word benzene in it. So you're gonna have a benzene ring. Okay, and it's gonna have a positive charge on a carbon outside of the ring. Okay, that's what a benzylic carbocation looks like. And this is the most stable carbocation formation, while this is the most unstable carbocation formation. Okay, so it goes this way. All right, so allylic, so benzylic and allylic, that suffix illic sound, that means it's resonating. So your charge, carbocation, radical, or negative charge, that means it has resonance involved, okay? And resonance is, yes, it's good for stabilizing your charges, okay? So that's a little tertiary, obviously we looked at before, which is just that. And then secondary looks like that. And then primary just looks like one carbon. And then, so yeah, don't get mixed with methyl and primary. You might think primary is actually methyl, but methyl, they will actually tell you, um, they will actually say CH3, okay, and the charge will be on the carbon, obviously, okay. Um, and vinyl, or sorry, okay, this vinyl is actually called vinylic. Let me scoop that over. Yeah. So it's not exactly resonating, but it does have a double bond. The only thing is the charge is directly on the double bond. Okay. And that's very unstable. Okay. For a positive charge, that's very unstable. Positive, radical, even negative, that's very unstable. Okay. Now, let me do the negative ones. Okay. So I'm not going to redraw it. I'm just going to type it out this time, since you guys already kind of know what it looks like. So for the trend for carboanion is very similar. You still have benzoic and then allylic, and then after allylic, instead of tertiary, it's actually primary. And instead of saying primary, I'm just going to write that first. So after primary, it's secondary, and then after secondary, it's tertiary. Um, sorry, even before primary, it's actually methyl. Okay. And after tertiary, again, it's going to be vinylic. All right, so that's the trend for carboanion. And then have you guys heard of bond dissociation energy, or BDE? Okay, so let me type it out. Bond dissociation energy. Okay, and it's noted as BDE. It's exactly what it sounds like. It's the opposite trend. So it's the energy it requires to dissociate a bond. Okay, the more stable a bond is, the less energy it requires. Okay, let me say that again. The more stable a bond is, and when I mean bond, I am talking about a radical bond. Okay, so the more stable a radical is, which means, using this trend, so the most stable is benzylic. So the benzylic would be the most stable structure, but it would require the least amount of energy. Okay, and let me type this out actually. So more stable equals less energy. Okay, as simple as that. Don't get confused by any other wording. Okay. And more often than not, they will tell you to rank by the highest bond dissociation energy, which means you have to go the opposite way. So the highest bond dissociation energy trend would be vinylic, methyl, and I'll just put M for it, and then primary, secondary, tertiary, allylic, A for allylic, and then B for benzylic. Okay. Oh, sorry. So this is highest. That's the trend for highest bond dissociation energy. Obviously, if it asks for the lowest, to rank by lowest, so if they say number one is your lowest bond dissociation energy, then you would go the opposite way, where benzoic is the lowest amount of energy because it's the most stable. And if they say number one is your highest bond dissociation energy or requires the most amount of energy, it's going to be vinylic, okay? And to talk briefly about like the science or the conceptual behind it, the more unstable a bond is, if it's like really unstable, if it's not willing to like react with anything, it's gonna require a lot of energy. Actually, most unstable means it is actually easy to react with, or it's like hyperreactive. Okay, so if you're hyperreactive, you're gonna have a lot of energy. So it requires a lot of energy to separate those bonds. Okay. Does BDE make sense? Because I know it can be very tricky. But if you just simplify it in these terms and use this trend, you should be able to do any ranking question. Yeah, of course. Okay, so BDE stands for bond dissociation energy. Okay, and to put it into a sentence, it's the energy that requires to dissociate a bond. Okay. Um, more specifically, a bond, like I said, is basically two radicals, okay, two electrons, okay? So that's why we are using the radical trend, the radical stability trend, okay? And that trend is benzoic, allylic, tertiary, secondary, primary, methyl, vinylic, okay? So where benzoic is the most stable and vinylic is the least stable, okay? This is the most stable for the radical to exist right here, okay? Because it can, it has lots of resonance. Here is directly placed on a double bond that creates a lot of instability, okay? And it's very reactive, okay? Because of that, more stability means less energy to separate those bonds. If you're perfect, you're stable, you have lots of resonance, it's not going to require a lot of energy to separate those two. Okay, it's very I guess low key, and yeah, but usually they're asking highest energy. Okay, in the question they'll be like number one, rank the following structures by highest bond dissociation energy, where number one contains the highest amount of energy. Because of that, and let me just write this out as well, less stable equals more energy. Okay, so it has a very inverse relationship. Okay, uh, and because of that, we have to invert our trend. Okay, does that make sense? Okay, perfect. Um, yeah, that's true. Dr. Stefan does place vinylic as more stable than methyl. So let me write that down. It's just I'm not sure if all professors do it. I feel like it's a very Dr. Stefan centric. So you might, if you're in her class, she might tell you to put vinylic as better than methyl. Okay. So I'll put that right here. And this is just how I learned it, ranking wise. So if you're in her class, then yes, do go follow that instructions. But if you're in another class with another professor, just follow whatever their trends are and their viewpoint on vinylic versus methyl for carboanion. Because like I said, every year, every professor has a different kind of rule book that they follow and what they deem is correct. Okay. All right. So that should be all of our trends. We'll get into SN1, E1, SN2, E2 trends next week, but they do have a similar trend. It's not as complicated as this, but yeah. So now we'll end today's weekly review with chlorination and bromination. Okay, and I'll do that at the bottom. So we'll first talk about chlorination and then bromination. Okay. So I am going to draw a random structure. Okay. So if they give me this structure, okay, maybe I should. No, it's okay. So if they give you this structure and the question says, give all the chlorination products and then give all the bromination products, and then they'll ask you to circle the most stable chlorination product and the most stable bromination product, okay? Obviously, because everything's multiple choice, that doesn't necessarily, the question might look a little bit different, the formatting might look different, but yeah. So the first thing you're supposed to do when solving this question is to find all the radicals, okay? When we're talking about chlorination and bromination, we're talking about radicals, okay? So remember, like I said at the very beginning, everywhere there's a hydrogen, there's one radical, okay? So the first step for me is to place a radical, and I'm going to do that in the color blue. Everywhere there's a hydrogen. Okay, so there's a hydrogen there, hydrogen there. There's a secondary carbon here, secondary carbon here, right here. Okay. Next thing I'm going to do is I'm going to label all of those radical positions. Okay, and I will label that in red. Okay, and when I mean label those positions, I mean using this. Okay, is it primary, allylic, is it vinylic? Okay. So first step is to put all your radical positions, then you have to label it, okay? Um, so let me, so this one is a primary. So I'll just put a 1. This one is a tertiary. This one is primary. This one is secondary, but it's secondary allylic. Okay, so 2A. This one is secondary, but it's vinylic. So 2V. This one is primary, but it's vinylic. Okay. Any questions on my red labelings? Okay. Obviously, it might take a little bit slower for you guys to do because you guys are still learning, but eventually you'll get to the position where you're able to do that very quickly. Okay. And the reason why these are vinylic is because these radicals are directly on carbons that contain a double bond. Okay. This one is a allylic because it's one carbon away from a double bond, which means that this radical can resonate. Okay, allylic means it can resonate. All right. This is tertiary because it's between 1, 2, 3 carbons, and these two are primary because they're only bonded to one other carbon. Okay. Are we all good so far? Any questions? We're almost done. We'll end early today. All right. Okay. So once you have so let me write these steps down for you guys. So first step, place a radical in all positions. Second step is to label those, label all radical positions. Okay. Now the third step is to find the most stable radical. Okay. So out of all of these positions, which one is the most stable radical position? Let me know in the chat. Okay, so I have 3, 2, 8, so the secondary allylic. But yeah, you guys are definitely correct. Compared to, a lot of people will get stuck between tertiary versus secondary allylic. Between benzylic and allylic, they have their own internal tertiary, secondary, primary. So tertiary benzylic, secondary benzylic, primary and benzylic, and then same for allylic, and then we'll get into tertiary. So even though tertiary is bigger than secondary, a secondary allylic position is much better than tertiary. Okay, so if it has resonance, it's automatically better than any of these positions. Okay, because it stabilizes, it spreads that charge across the whole molecule. Okay. So yes, 2A is our most stable radical position. Okay, and if we're answering bromination question, and sorry, I'm kind of getting ahead of myself and kind of jumping all over the place, but this is what you'll see. The actual reagent is chlorine 2 light, which is HV, and then bromination is Br2. Okay. So it's not looking good. Let me just type it. Br. This is. Yeah, this is Br2. Okay. And the reason why we have Br2 and Cl2, like the reason why we have two of them is because something called initiation, propagation, and termination, which I really don't want to get into. I would refer to your slides. It wasn't heavily emphasized in the past years, but because everything's on virtual and online, it might be changing. So I would just quickly glance over it, maybe read the textbook or watch a YouTube video on it. But other than that, I wouldn't worry too much about it. I would place most of your attention on everything else, and then if you have time, then go back and learn about that propagation, and then termination. Okay, this is kind of like to explain like how mechanisms work. But if you guys got to this step, then you already basically understand this. Okay, so if when answering this question for bromination, we have to redraw the structure. And then we would place, bromine would come in and attack right here at that carbon, and then our answer would be bromine right there. Okay, this is called bromination. Okay, bromination is more selective than chlorination. Okay, chlorination has multiple products, or all possible unique products, but bromination has only the most stable product. Okay? Sorry. So someone asked, would you also put a bromine atom radical beside it, or are they only looking for that structure? Yes. So you only have to draw this. Okay, this is considered your major product. The bromine radical is a secondary product or a byproduct. You don't have to ever draw that. Okay. But once again, because it's multiple choice, I don't think they'll show that option, so don't worry about it. You only have to draw this. Okay. Now, so hopefully you guys understand bromination. You're only drawing the most stable product. But for chlorination, you have to draw all of them or pick all of them in your multiple choice. Okay. And let me draw all of them. Okay. And when I mean all of them, I mean all of the unique ones. Okay. So the primary one, tertiary one, secondary one. Okay. And normally they don't necessarily write one of these positions. So I'm just going to focus on these three. Okay. Also, a little side note is this primary and this primary are the exact same. Okay, so these are not unique. Okay, that's why I only included one of these and not the other. And the reason why they are the same and not unique is because there is kind of like a line of symmetry where if you flip it, you get like kind of like the exact same thing. Okay. Um, So I'm not going to draw everything, or I'm not going to redraw the entire structure like 3 different times, but I'm just going to write it on here, and I'm going to choose orange. So each of these, you would draw chlorine right there, and then redraw your structure, and then you would put chlorine right there, and then redraw your structure, and then you would put chlorine right here. Okay. Um, Technically, these are unique as well. So if they have those options in your multiple choice, then by all means select it. But from what I've seen, they usually only look for these 3 positions. Okay, but just uh, refer to like your practice quiz and practice exams for what they want. Okay. All right. So it's 250. That should be all of our content for this unit or for this week, weekly review. Once again, we went over exam 1, exam intro to exam 2, chapter 4, which is all of our mechanisms or like intro to mechanisms and the trends, bromination, chlorination. Okay. Do you guys have any questions about anything that I've done so far? Or today, rather? Okay. Yeah, no problem, of course. Um, is there anything you want to see an example of, or you guys want me to elaborate? If not, we can end it here. No need to continue it, as we'll get into that next week once you guys learned it in lecture. Okay. Yeah, of course. Thanks for coming. No problem. Yeah, I highly recommend just taking a screenshot because everything's online. It's easy just to take a screenshot and refer to your notes and maybe rewrite it in your own notes. Um, yeah. All right. I'll see you guys next week.